Hello, calculus students. We're going to be taking a look at a BC problem that resides here in Chapter 10 of the Larson 9th edition textbook. So anybody who's working with parametric equations and calculus, particularly in finding surface area, might be interested in taking a look at this. This is actually example 6 from the Larson textbook, section 10.3 that my students here at Avon High School will be studying. And I would like to begin this example by discussing the contents of Theorem 10.9 that you can see here on your screen. Basically, in this theorem, you're given the formulas for the area of a surface of revolution. And we'll read this together. It says, if a smooth curve C is given by the equations x equal f of t and y equal g of t, such that C does not intersect itself on the interval from A to B, then the area S of the surface of revolution formed by revolving C about the coordinate axis is given by the following. And notice we do have two options here. We've got an equation for a revolution about the x-axis up at the top, and then an equation for the revolution about the y-axis. Now you should have already been exposed to surface area in terms of rectangular coordinate systems, and remember that you have a very similar looking formula. But the two are very related by the fact that in essence what you are taking into consideration is the fact that you are taking 2 pi times a radius, and that's what your equation g of t will mean when you revolve about the x-axis, because g of t is equal to the y. It's a vertical distance from the x-axis. So you've got 2 pi times your radius times what we've referred to in the past as the length of a frustum, which is sort of a small segment, an infinitesimal segment of a portion of your particular three-dimensional shape that does get its revolution and taken into consideration. So you've got it 2 pi times the integration of a radius times the distance in either case. So let's take a look at a specific example here, number 6, and let me get my pen ready to go. What we've got is C being the arc of the circle, x squared plus y squared equal to 9. And we have that particular arc graphed from the coordinates 3, 0 to not so pretty of a coordinate, 3 halves, comma 3 radical 3 over 2. We want to find the area of that surface formed by revolving C about the x-axis. So you've got this sort of outer shell of, I don't want to call this a half sphere because I don't mean for this to be perfectly spherical and to make a perfect semi-sphere. But we could sort of use that terminology just to kind of put it in some context. So what we need to do here is put together an integration that's going to take care of this. But more importantly, we want to try to throw this into the world of parametric equations as much as possible. So that's going to be very important. So first of all, parametrically, what two equations for y and x work wonders when you're dealing with parametric equations, especially ones that might involve shapes that look somewhat like this x squared plus y squared equal 9, this circle, if you will, with a radius 3. Well, x equaling r cosine of some parameter, in which case we'll use t here, where y is r times the sine of t. And specific to this problem, the r value is 3. Now that is a very common substitution that you're going to make to move from the world of rectangular coordinates into the parametric equation world. Now we have an issue with what are we going to do about our boundaries. Because in order to begin our surface area formula, and we could begin, we could write S equals and have our 2 pi involved in there, and then our integration symbol, and then in fact, we could go ahead and fill out the rest of our integrand. Why not? If we're going to revolve around the x-axis, then we sort of have a representative rectangle that might look something like this. So that is definitely going to be a value that involves, what is the distance of a y here? Well, y is just called 3 times the sine of t. And then we finish it off with the length of our frustum, which is just, like I said before, a representative of the length of a segment that would be a top of that rectangle. And according to our formula from above, we just simply take the derivative of our x, square it, and add that to the derivative of our y squared. So the derivative of this 3 cosine of t, which I could work it out over here, dx dt, of course, would be negative 3 times the sine of t. And while we're at it, we can go ahead and write dy dt to be 3 times the cosine of t. And we'll square each of those and place them inside of our radical. So there we have it, our definite integral minus the boundaries. And I say this to my classes quite a bit. Sometimes when you're dealing with parametric equations and even polar equations, it's that pesky t value sometimes that really gets in the way. It's that parameter. We have lots of great information about ordered pairs of x and y, but we just don't know a whole lot about t, and that's our goal right now. We need to figure out what is the value of t right now when we're at that point 3, 0. Well, we can figure that out by simply going to our parametric equations right here and saying, okay, if x were 3, and I'm going to do that work here off to the side, if x were 3, what is t going to be in this equation? Well, of course, you divide both sides by 3, you get 1 equal cosine, and when you take the inverse cosine of 1, you'll notice that your value of t would be 0. Well, if you take a look at the other equation, if you want to verify that, using the ordered pair 3, 0 once again, but this time using 0 for the y, you'll come up with the equation 0 is equal to 3 times the sine of t. Well, what was t going to be here in order to make this equation true? And you'll find out that it's just the same. So really, you only have to plug in your ordered pair into one of your two parametric equations, as long as you do your algebraic or trigonometric work correctly. So when we are at the ordered pair 3, 0, our t value is quite clearly 0. Now, perhaps it might be a little bit more challenging dealing with this other ordered pair up here. And you can choose to use the 3/2 or the 3 radical 3 over 2. Since the 3/2 seems to look a little bit easier on the eyes, I may go with that, knowing that that's my x, and that would be equal to the 3 cosine of t. By the time I divide both sides by 3, I'll have 1/2 equaling the cosine of t. And when you think about this, what angle measure do you take the cosine of to give you a half? Here, if you need a picture, we can figure that out. If that angle there is t, cosine is adjacent over hypotenuse, well, we're talking about the angle that would essentially be opposite of a radical 3 side length, and that would be a 60 degrees, or pi over 3 in this case, and that is our upper boundary. Maybe I should finish that off over here as well. T is pi over 3. And I think we're all set to go. Now, a lot of times with these problems, you kind of question, okay, are we going to be able to integrate these without the use of a calculator? Well, a lot of times the applications that you would see in parametric and polar do produce some very ugly integral expressions that are very difficult to do by hand. This particular problem is not so much the case. I would say that this is the type of problem that one could easily encounter on a no calculator multiple choice portion of the AP exam. So if we continue with this, we would find out a couple of things, like the fact that this 3 coefficient could factor out or bring itself out to the front of the integral, as well as a square root of 9 that can be factored out. Now that square root of 9 will come out and essentially become a 3 multiplied by that 3 multiplied by that 2 pi, in essence will give me 18 pi. Excuse me. So what's left? Well, we still have an integration symbol with the boundaries, and then a sine of t along with the square root of the sine squared plus the cosine squared. The square root of sine squared plus cosine squared. You can't get much easier than that. That's just simply equal to 1. And the square root of 1, of course, is 1. So all that remains in the integrand is the sine of t with respect to t. Very easy to integrate. Integration of sine of t, of course, is going to give us negative cosine of t. Right? Remember, whenever you integrate and your answer that you get starts with the letter c, you want to have a negative sign in front of your answer. So we have negative 18 pi times the cosine of t, and our boundaries are still going to be pi over 3 to 0. So we plug those in. I'll sort of factor out the negative 18 pi. So we have to evaluate the cosine of pi thirds and subtract the cosine of 0. Well, the cosine of pi over 3. Once again, if we take a look at the picture over here in the lower right corner, the cosine of 60 degrees is 1/2. And the cosine of 0, you can figure that out a lot of different ways. Unit circle, look at the graph of cosine, which I think is the easiest. And that, of course, is 1. And this is actually a good situation because I was hoping that we would get some kind of a negative value inside of these parentheses. Otherwise, that doesn't loom very well for our answer because our answer should be positive. So we end up with negative 18 pi multiplied by negative 1/2, which gives us an answer of 9 pi. 9 pi, we don't really have a unit to attach to this. We could say square units if we wanted to be precise. But that essentially will tell you exactly how much space is occupied by the outer part of that figure once it's revolved around the x-axis. Of course, you could easily take this particular integrand that you have right up here, and it could be entered into any type of graphing calculator that would accept numeric integration, and you could see that the answer would indeed be 9 pi.